Hello, my name is Elizabeth Wyss, and today I'll be presenting me and my colleagues' work on Parcae, a blockchain-based PRF service for everyone. I want to begin this talk with a brief overview of the contributions of our work. So Parcae is a secure, publicly distributed password hardening service constructed on a blockchain. Importantly, Parcae resolves the challenging and inherent security trade-offs between PRF privacy and blockchain verifiability. Parcae additionally preserves the existing security guarantees of state-of-the-art password hardening services, and moreover, Parcae achieves additional security guarantees ensured by the underlying blockchain. In discussing passwords as an attack vector, password security is still fundamentally broken. Industry standard password management involves hashing and salting passwords. However, these practices offer insufficient protections in case of database compromisation. Hashed and salted passwords are extremely vulnerable to offline brute force attacks, including dictionary attacks, and we know that this problem is still very relevant. In 2019, Verizon studied 450 instances of disclosed data breaches that involved the breach of user credentials, involving passwords stored in various formats. Ultimately, we see Parcae to be the next step in the evolution of password hardening schemes. In the early days, passwords were often stored in plain text, and this is extremely dangerous in the case of password database compromisation. Then came the ideas of password hashing and salting, which offers some protections for compromised passwords. However, they're still quite vulnerable, especially in the case of offline brute force attacks. Then came the invention of pseudo-random function, or PRF services, which use remote encryption keys to make password cracking much more difficult. After that, there were some innovations in the idea of a partially oblivious PRF. This adds additional security guarantees to PRF services. However, there's still some big limitations in partially oblivious PRFs that have prevented widespread adoption. And so we address those limitations in Parcae to fully realize a secure, publicly distributed PRF service. Now, I want to provide a brief overview of how primitive PRF services function. So an end user will interact with a client service as normal, trying to log in by providing their username and password. The client service will then calculate a hash of the user's password with some per user salt value. And instead of using this hash for password verification purposes, the client will send the hash to a remote PRF service. The remote PRF service then encrypts the hash with a locally stored key and then returns that encrypted hash to the client service. So now the client service can use an encrypted hash for user password verification purposes. This is really nice because it introduces layers of security to stored passwords. Now, if a password cracking adversary wants to compromise some passwords, they need to steal this password database, but they also need to compromise the remote key of the PRF service, and this is much harder for them to do. Next, I discuss partially oblivious PRFs, or PO-PRFs. These improve primitive PRFs with additional security benefits, including multi-client servicing, which allows multiple clients to use the same PRF service, each with their own secret key. There's per-user rate limiting, which allows us to detect online attacks, since a password cracking adversary that's trying to use the service to reason about passwords will have to make repeated queries that share per-user information. We also get secret key rotation, which allows us to cryptographically invalidate stolen password databases, and also zero-knowledge proof verifiability, which allows a client to verify that an encrypted password hash is calculated correctly with respect to a public key known to them. All of these features combined enables publicly distributed PRF services, ones that allow any anonymous user to harden passwords with ease. Using one of these PRF services is as simple as installing a library and interacting with the PRF service through that library. This enables fast, easy deployment. Now I discuss limitations in PO-PRF services that are inherent to the publicly distributed domain. One is that clients must expand their root of trust to contain a third-party PRF service, and this third-party PRF service is not incentivized to behave honestly. Additionally, a PRF service would serve as a single point of failure along the critical path of user verification. This would mean that a denial of service attack could prevent all clients from being able to perform user authentication, which would be devastating. So as far as overcoming these challenges, we identify blockchains to be a security primitive that provides the trust, availability, and scalability needed to address these issues. Our approach for Parcae is to address the weaknesses of state-of-the-art publicly distributed PRF services through the use of a permissioned blockchain. Now, this inherently poses some challenging security trade-offs, since PRF services need to conceal information to provide privacy, and yet blockchains need to expose information to provide verifiability. We find that audible permissioned blockchains can overcome these inherent trade-offs through some clever applications of cryptography. To realize our design goals, Parcae implements partially oblivious PRFs on a permissioned blockchain. What's nice about this approach is that it preserves all of the features of existing state-of-the-art PRF services. Additionally, Parcae achieves security guarantees needed in the publicly distributed setting, including honest protocol adherence, constant availability, and service auditing capabilities. In total, these features overcome the limitations of existing publicly distributed PRF services to realize our goals. I now discuss what is honest protocol adherence and why it's needed in Parcae. The main question behind honest protocol adherence is how can we ensure that a service does what it claims to do? This is an issue since an opaque service could behave dishonestly to, say, cut costs, and this would invalidate the integrity of the service. This is important in Parcae because we need to maintain the integrity of the password hardening service so that passwords stay secure. Now, the solution to address honest protocol adherence is to provide incentives to behave honestly and to make the protocol transparent. To realize this solution, the Parcae PRF protocol is implemented on a smart contract residing on a private permissioned blockchain. So the Parcae blockchain is constructed using Hyperledger Fabric, which is an open source blockchain framework where all blockchain transactions adhere to smart contract definitions. These smart contract definitions are enforced for integrity by the underlying blockchain framework. And this means that Parcae's protocol is transparent to all participants, and it's also correctly enforced by the underlying blockchain framework, ensuring that the protocol is adhered to honestly. Another consequence of this is that even if the Parcae blockchain were to be compromised by an adversary, the Parcae protocol could not be altered without transparently notifying all participants. Next, I'll discuss constant availability and why it's needed in Parcae. The main idea behind constant availability is how can we ensure that a critical service is always accessible? This is an issue since critical service downtime disrupts the workflows of all entities that rely on the service. In the case of Parcae, any downtime in Parcae would prevent all of its clients from performing user authentication for the entire duration of the downtime, and this is devastating for client services. So the solution to address constant availability is to provide dynamic scaling of a service and also fault tolerance so that the service is reliable even in the case of failure. Parcae achieves constant availability because the Parcae blockchain consists of multiple fault-tolerant peers that each serve as separate queryable entities. When multiple clients all make queries to the Parcae blockchain, these queries are distributed amongst Parcae's peers. When these peers do not have enough throughput to meet the needs of all of Parcae's clients, the peers are dynamically scaled up in quantity to ensure that the service is constantly available. This will prevent denial of service attacks because Parcae simply scales to meet the requests of the denial of service attack. In addition, these peers are fault tolerant, which means that if any of them go down, data integrity is still preserved, thus preserving the accuracy and integrity of the Parcae blockchain, even through adversarial influence. Now I'll discuss what service auditing is and why it's needed in Parcae. The main question behind service auditing is how can we ensure that our interactions with a service are legitimate? This is an issue because illegitimate services could masquerade as legitimate ones without the presence of service auditing. This is particularly a problem in Parcae because an illegitimate service could fake a client's registration with Parcae, and this would allow the illegitimate service to falsify clients' queries even through zero-knowledge proofs, since the illegitimate service would then control the client's public key. Now, the solution to this is that we need clients to be able to participate in the service and inspect the service in real time. Parcae realizes service auditing capabilities by allowing clients to participate in the Parcae blockchain. Parcae clients can optionally operate a blockchain auditing node that receives a hashed version of the entire Parcae blockchain ledger in real time, including the hashed read and write sets of every transaction occurring on the Parcae blockchain. This auditing capability enables clients to verify the data hashes within transactions initiated by them, thus ensuring the legitimacy of their interactions with Parcae. At the same time, these clients cannot reason about the hashes of transactions initiated by clients other than them, thus they are oblivious to information that they should not know. Now that I've described the core features of Parcae, I want to give a brief overview of the architecture of Parcae. So in Parcae, clients issue requests to intermediate servers. These intermediate servers possess the cryptographic material necessary to interact with the Parcae blockchain and forward these requests onto the Parcae blockchain. The Parcae blockchain then performs security-relevant operations and calculations and returns the output to the intermediate servers, which can then return the output to Parcae's clients. What's nice about this approach is that the intermediate servers merely provide input filtering. They don't alter the Parcae protocol in any way. In addition, all data that is security sensitive is blinded in transit from client to server, from server to blockchain, and vice versa, which helps protect information in transit. Next, I'll describe the Parcae front-end API that clients can interact with. First, clients must register with Parcae in order to use the service. Upon successful registration, clients will receive a unique ID and public key that they need in Parcae. Next, clients can begin to query Parcae by providing their ID, a password hash, and the salt value of that password hash, which will return Parcae's PRF query result, which is the encrypted password hash. If a client detects that their password database has become compromised, they can rotate their secret key by first generating an authorization token by providing their ID. This will send the token to the client out of band, such as through an email address. After that, the client can provide their ID and that authorization token to rotate their Parcae secret key and return an update token. This update token can then be applied to any previously stored password hashes, which will allow them to be encrypted under the new key without any end-user input. And lastly, Parcae offers clients the ability to audit the Parcae blockchain, and this will return the cryptographic materials necessary to operate a blockchain auditing peer. Now I'll describe Parcae's formal query protocol, which relies on the BN256 elliptical curve bilinear pairing. First, the client calculates H, which is a hash of a password and salt value. The client will then calculate R, which is known as a blinding constant, defined to be a secure random number on the order of the BN256 elliptical curve. The client then calculates a blinded hash X, which is defined to be H raised to the power of the blinding constant R. The client then sends this blinded hash, as well as the salt value and their ID, to a Parcae intermediate server, which forwards that to the Parcae blockchain. The Parcae blockchain calculates the client's secret key as a hash of a central secret stored on the blockchain, as well as a pre-key value unique to the client, thus ensuring that the client's secret key is unique to them. The Parcae blockchain then calculates Y, which is a BN256 bilinear pairing of the blinded hash as well as the salt value, all raised to the power of the secret key. This blinded encrypted hash is then returned to the intermediate server, which is forwarded on to the client. The client lastly calculates Z, the final output, by raising the encrypted blinded hash to the inverse of the blinding constant. Because the BN256 elliptical curve bilinear pairing preserves exponentiation, this will cancel out the blinding that was performed before the input was sent to the intermediate server in the first place. This is nice because now the intermediate server and blockchain will only ever see blinded sensitive information. Next, I'll describe the experimentally evaluated performance and scalability of our prototype implementation of Parcae. We find that a single Parcae blockchain peer can provide queries with a latency of 40 milliseconds and with a throughput of up to 498 queries per second. We find that this latency of 40 milliseconds tends to stay relatively constant as peers are dynamically scaled up in quantity. And we also find that this throughput tends to scale linearly as peers are dynamically scaled up in quantity. We note that this approach is much faster than other historical forms of password hardening, such as iterated hashing. One example of an iterated hashing protocol was used in Apple's iTunes verification process, and this iterated hashing approach incurred more than 6 times the latency of a single Parcae query. Lastly, to conclude this work, Parcae strengthens and extends upon state-of-the-art PRF services by augmenting them with the security guarantees of blockchains. Parcae overcomes the limitations of existing PRF services to fully realize a secure, publicly distributed PRF service. And Parcae is highly scalable and offers reasonable performance with respect to past password hardening approaches. Thank you.